Okay, let the lecture begin. Today I will briefly be presenting on key concepts from ISLP Chapter 5, Resampling Methods. Resampling methods are indispensable tools in modern statistics. They involve repeatedly drawing samples and repeating models to obtain additional information such as models' variability. While historically and computationally expensive, recent advances make them widely accessible. I will talk about two main common methods of resampling methods. One is cross-validation, and the another one is Bootstrap. Cross-validation is a resampling method for model assessment and model selection, and Bootstrap is for measuring the accuracy of parameter estimates. I will explain more details later. The first one is cross-validation. Cross-validation is a resampling method primarily used to estimate the test error rate of statistical learning model. As I mentioned before, cross-validation is proper for model assessment and model selection, and this kind of estimating test error rate is essential for that purpose. In this book, ISLP explains three kinds of constructing valid data set. The first one is validation set approach. It is really simple method. Just split the original data set into two subsets. One is for training set and the another one is validation data set. So if we see this figure, we have n numbers of original data set and split them into two parts, blue one and the orange one. The blue one uses for the training data set, and the another orange one might be used as validation data set. The main point we have to see here is randomness. It means if we see the numbers in blue data set, while the original data set is arranged by in order of number, if there's random numbers in data set. So this makes some drawbacks such as high variability and potential overestimation of the test error. So to improve not just simple dividing in two data sets, the next method suggested, its name's leave one out cross-validation. If we see the figure, unlike the before case has only one split and one case of failing, but the one out cross-validation have n times of failing. The n is for the size of the original data set. And each failing, a single observation, used as the validation set, and the other n-1 number of observation uses as the test data set. So in here, this orange boxes, orange observations used as the validation set, and the blue other remaining data set uses the test data set. This will reduce, so there is no randomness, so just only simple valid data set. So there is no randomness, it makes less bias. But there is also some drawbacks. So it repeats n times because the dataset size is n. So let's suppose that what will be happen if the dataset or the size of the original dataset n increase extremely. Then feeding the number of repeating times increase, then and it will cost computationally expensive on large datasets. So another method, the K-forward cross-validation is suggested. It's not that big it's not showing that big difference between leave one out cross-validation, but unlike the using only one observation, only one single observation as the valid data set, K-fold cross-validation uses uh, subset as the valid data set. And each subset is just dividing the original data set into K groups. K is from here. And leave one out cross validation. It repeats K times fitting and one fourth, this orange subset is called fourth, one fourth for validation set and another K minus one fourth for the test set. So this will reduce the cost for dataset size n, but if we see in the validation dataset element, there exists randomness in Ford, unlike leave one out cross validation. Okay. The second one is Bootstrap. Bootstrap is a powerful and widely applicable resampling technique used to quantify the uncertainty associated with a statistical estimator or prediction method. This allows us to estimate the standard error and confidence interval for statistics when analytic methods are impossible or they are too complex to calculate. The main goal of Bootstrap is estimate the sampling distribution and accuracy, and it is a non-parametric method, meaning it does not require assumptions about the underlying distribution of the data. Uh, so look at the figure. It is a simple brief for the Bootstrap process. The bootstrap process follows three steps. First one is resampling, and then estimation, and finally accuracy estimation. In the figure, there exists the original data G, Z, and repeatedly draw B, the sub data set from the original data set. Each size of n, and there is also some replacement. If we see here, the Z contains 1 to 3, but some contains 3, 1, 3, and some contains 2, 3, 1, and some contains 2, 2, 1 like this with replacement. Each of these small data set called as a bootstrap data set. And from each bootstrap data set, we can calculate the statistics of interest A hat, called as A hat. Then we can calculate the standard error of the original estimation. Or original estimate is we can calculate the standard error of the original estimation throughout this B bootstrap estimate throughout at this B bootstrap standard deviation through this formula. So let's see the problems. We have to prove that alpha equals sigma's. We have to prove that alpha equals to sigma x squared plus sigma y squared minus 2 sigma xy over sigma y squared minus sigma xy minimize the variance of alpha x plus 1 minus alpha y. So to get the alpha value, then minimize the variance of alpha x plus 1 minus of alpha y. we have to calculate. We have to calculate this into the alpha form. So variance of alpha x plus 1 minus alpha y equals to alpha square, sigma x squared plus 1 minus alpha square, sigma y squared plus 2 alpha 1 minus alpha of sigma of xy. So, so to get the minimum value, of variance of this, minimum value of this, we have to differentiate this. If we let this f of alpha, we have to differentiate f of alpha with respect to alpha. So if we differentiate this variance alpha x plus 1 minus alpha of y with respect to alpha, then we can get this kind of form. This is ISLP, but it's called f prime of alpha. So we have to find the alpha value that minimize the variance of the f alpha. So we have to find the alpha value that makes f prime alpha becomes 0. So if we suppose that this f prime alpha equals to 0, then we can get the alpha value as sigma x squared plus sigma y squared minus 2 sigma xy over sigma y squared minus sigma xy. So it means this value will make variance as minimum, but also we can make the variance value as maximum. So we have to find out that this alpha value makes minimum. This alpha value, this alpha value will makes the variance of alpha x plus 1 minus alpha is minimum. So we have to differentiate f prime of alpha again, and we have to find out that this is bigger than 0 or less than 0. So if we differentiate the f prime of alpha again, we can get 2 times of sigma x squared plus 2 times of sigma y squared minus 4 times of sigma xy. And this is also positive. This value is always positive because it is equivalent to the variance of difference between the two vectors, the variance of x minus y. So this is always bigger than 0. So then alpha makes the minimum. Alpha is the value alpha. This value is the value that makes the variance of alpha x plus 1 minus alpha y as a minimum. So we can get this alpha value by calculating statistically, but it might have variability and uncertainty because the formula for alpha hat is complex and analytically calculating its standard error might be extremely difficult. This is precisely where the bootstrap becomes indispensable. The bootstrap provides the only practical way to quantify the accuracy and uncertainty of our proved optimal portfolio weight, alpha hat, by simulating its sampling distribution. Okay, this is end for the lecture, and thanks for listening.